should share the screen. Virtual claps for Charlotte. And Diego will talk about Wilson line as one-dimensional defects. Well, with something in. Diego should be unmuted.
Yeah, can you hear me now? Let me.
Yes, yes.
Can you see me now? Probably. Okay. Well, let me, of course, thank the organizers for the chance of participating in this IGST workshop. So, well, the addendum in the title is just to be a little bit more precise. Since today I'm going to be talking about mixed boundary conditions in ADS2 and its interpretation of the holographic description of one-dimensional defects, Wilson line defects. So this is mostly based on the work I have done in collaboration with Victor Giraldo Rivera and Guillermo Silva. So, well, the plan is I will just begin present for you this interpretation of Wilson lines of one-dimensional defects and discuss a bit the relation between excitations along this line and the fluctuations on the dual worldsheet description. And then I will, as I said, focus and concentrate on the mixed boundary conditions for this fluctuation on the worldsheet. And I'll try to apply some of these ideas for the case of Wilson lines in AVJM theory. So, okay, I could say many things to motivate the study of Wilson loops in general, but today, to be precise, I will just emphasize that if you would like to define the conformal data in a CFT, you have to consider both local operators and defects. And in this regard, Wilson loops are just an example of one-dimensional defects. So that's what I wanted to say. So without further ado, the problem I'm going to be discussing today is the consideration of a one-dimensional line defect in a d-dimensional conformal field theory. So when you do that, of course, the conformal symmetry, this OS2, D, is going to be broken. But in some situations, it's not completely broken. So the best you could hope is that to preserve the conformal symmetry along the line and rotations along the transverse directions to the line. An example of that conformal line is the half BPS Maldacena Wilson loop in L=4 super-Young middles. So in that example, in addition to the conformal symmetry in the line and transverse rotation, you have this additional SO5 internal symmetry altogether with 16 supersymmetries, giving rise to this OSP4/4 supergroup. So since you would like to consider a theory, in the line, we need some notion of correlation function of excitations along the line. And you can get that notion by just computing the expectation value of this Wilson loop, but with the insertion of N=4 super-Young middle operators along the line. So, and then with this definition of correlators, okay, if the theory if the line is conformal, these correlators are going to be constrained by conformal symmetry in the usual way. So, okay, then the question I would like to raise now is what kind of operators it is interesting to insert along the line. Well, whenever you are talking about a defect, something which is very relevant to consider is the displacement multiplet. In the case of this line in N=4, the displacement multiplet it contains 5 components, which are just the transverse scalar fields. 5 of them, they have insertions with the scalar dimension delta =1. And also you have 3 the 3 transverse displacement operators transverse to the line. And they have the scale dimension =2. And you have also 8 fermionic insertions with scale dimension 3/2. So they are called displacement operators because you can use them to characterize small deformations of the line with inserting them along the line. So, and moreover, even if you were able to, in principle, you can consider coherent insertion of many of these displacement components to account for the most arbitrary Maldacena Wilson loop. So but today, as I said, I would like to focus on the holographic description of this setup. So I need to remind for you that in the context of the ADS-CFT correspondence, Wilson loop are described in terms of open strings ending at the boundary of ADS. And in the case of the Wilson line, we have this worldsheet ending at the line at the boundary of ADS. And when you look for the minimal area configuration, you get that this worldsheet is an ADS2. So, and then when you ask what are the dual representation of these displacement components on this worldsheet, they are nothing but the fluctuations on this ADS2 worldsheet in the static cage. When you compute the spectrum of masses for the fluctuations on this ADS2 worldsheet, you discover that the spectrum of masses matches precisely the spectrum of scale dimensions of the component of the displacement multiplet when you follow this the usual ADS-CFT relation between masses in the bulk and scale dimensions at the boundaries. But today, I would like to discuss some other kind of insertions, some insertion of some operator which is not part of the displacement of multiplet. So in this, in order to motivate that, let me consider this interesting Wilson loop proposed by Polchinski and Sully. It's a sort of interpolating Wilson loop, interpolating because it has this arbitrary parameter zeta here in the coupling with the scalar field. So if you set zeta equal to 0, this is the ordinary Wilson loop. And when you set zeta equal to 1, this is the Maldacena Wilson loop, or Wilson-like. Well, it depends on the curve. As I said, this is related to the insertions of phi-6, of these phi-6 scalar fields, which is not part of the displacement multiplet, because you can write this interpolating Wilson loop. You can expand in powers of this 1 minus zeta, and then you see that you can write this operator as insertions of phi-6 along the Maldacena Wilson loop. Okay, what it is funny about this Wilson loop is that when you compute its expectation value, so you realize that this parameter zeta requires to be renormalized, so it runs, and then you can compute the beta function associated to its running, and you get this. So what you realize that you have here is that you have like a renormalization group flow in the theory defined along the line. So by looking at the zeros of this beta function, you find this fixed points. You have this UV fixed point when zeta is equal to 0. When zeta equal to 0, recall we have the ordinary Wilson loop, and when you are there, this phi-6 insertion, its scale dimension is 1 minus a little bit, that's perturbatively. So it's the insertion of a phi-6 is irrelevant. The formation of the theory, so it triggers an Archie flow that takes you all the way to this other fixed point when zeta is equal to 1, when you have this Maldacena Wilson loop. So, okay, what is the dual description of this? Let us first consider the dual description of the endpoints of this Archie flow. Recall that when you're in the Maldacena Wilson loop, the dual string is fully localized in the phi sphere. So you have to impose Dirichlet boundary condition for all the angles in the phi sphere. On the contrary, when you're in the ordinary Wilson loop, the dual open string is completely delocalized in the phi sphere. So you have to impose Neumann boundary condition for all the angles of the phi sphere. So somehow you expect that this interpolating Wilson loop is dual to some sort of interpolating or mixed boundary conditions. And that's not so surprising. So it's an old idea of ADS-CFT that you could represent Archie flows driven by multi-trace deformations using mixed boundary conditions on ADS. So this is an idea by Witten. This is the general case, but that's the idea that Polchinski and Sully, they took that idea and applied for the phi massless scalar fields associated to fluctuations along the phi sphere. So you have these files. So this is just like the expansion of this a massless scalar field in ADS2. So alpha and beta, like the functions giving the two admissible behaviors. In this example, for massless field in ADS2, delta minus is equal to 0 and delta plus is equal to 1. So these are the two possible behaviors. What Polchinski and Sulik did was just to consider like a quadratic boundary term leading to this like a boundary condition, which is like a linear combination of alpha, chi alpha plus beta equal to 0. Say if you impose alpha equal to 0, that would correspond to the Dirichlet boundary condition, while if you impose beta equal to 0, it's like demanding the normal derivative to be vanishing. So, but what I propose is this linear combination, and then you see that why it is reasonable that this is not conformal, because this parameter you are using to define this boundary condition is dimension full, so you are introducing a scale, and it also breaks supersymmetry. So, but okay, so far this is more or less an introduction or a motivation to the problem we actually consider in the work I mentioned at the beginning. So what we wanted to do was to apply some of these ideas to the case of Wilson lines in ABJM theories. So ABJM theories are these Chor-Simon theories, where this quiver depicts more or less the field content of the theory. Of course, you have a half EPS line in this theory. It is written as the exponential of this superconnection. You see it's a little bit more complicated because you have the two gauge fields here. You also have the coupling with the scalars and also fermions. Okay, and here you have the symmetry of the line. You can consider, you could study as before a theory defined along this one-dimensional line. You can study the displacement multiplet, and this has been done in various papers. Some of them are here. So, but let me just try to stress the main differences with the cases I reviewed before of the line in n=4 superunions. So when you go to the dual description for these Wilson loops, again, you found an ADS2, but in this case, this ADS2 worldsheet is extended in ADS4 times CP3, which is the dual background in ABJM theories. And then because of that, when you compute a spectrum of masses for the fluctuations, this is a little bit different. So in this case, you get 6 massless scalar fields corresponding to the fluctuations along the CP3. You have only 2 massive scalar fields. Those are the 2 transverse ADS2 fluctuations. And when you consider the spinor fluctuations, 6 of them has mass 1, but now you have 2 massless spinor fluctuations. And let me stress that because this is the crucial difference with the previous example. So having massless fermions is crucial to find supersymmetric boundary conditions other than Dirichlet. So, and eventually, ultimately, this is the reason why, or this is related to the reason, related to the fact that in ABJM theories, there is a richer family of PPS Wilson loops you could define. So as a matter of fact, you can define a 1 parameter family of Wilson loops in ABJM theories. So this is, in that case, is defined through this superconnection. So you see, it's more or less what I've written before, but now we have this parameter zeta here in the coupling with the fermions, and also is somewhere inside this matrix M that gives the coupling with the scalar fields. So, and it's important to emphasize that this Wilson loop is supersymmetric, preserving 4 supersymmetries for any value of this parameter zeta. When you set zeta equal to 1, this is nothing but the previous superconnection, or the half EPS line I presented before. And when you set zeta equal to 0, this is like the original bosonic 1,6 PPS Wilson loop. And okay, we were interested in the dual description of that. When you consider the dual open strings for the half EPS Wilson loop, again, you find you have an open string which is fully localized in the CP3, so you have to impose Dirichlet boundary condition on all the angles on the CP3. But when you consider the dual description of the bosonic 1,6 PPS Wilson loop, you find, according to following the symmetries of the internal symmetry which are preserved, that the open string has to be like delocalized on a CP1 inside the CP3. So the proposal is that you have to impose 4 Dirichlet boundary condition in 4 the CP3 angles, and Neumann in the remaining 2. So somehow you kind of expect that the dual of this Wilson loop has to interpolate between Dirichlet and Neumann, but revealing the precise interpolation, the precise form of this mixed boundary condition was our motivation. And in order to find it, we are going to follow like two restrictions. One of them is this has to be supersymmetric, and also we don't want it to this mixed boundary condition to break the conformal symmetry. The reason for that is that in spite this Wilson loop depends on this parameter. When you compute expectation value, the expectation value is independent of zeta. And then if you interpret the expectation value of the Wilson loop as giving the free energy of the one-dimensional theory, this independence is indicating that this should correspond more to a marginal deformation than to an Archie flow of the one-dimensional theory. So what we have to do, sorry, is to study supersymmetric mixed boundary conditions in IGST. So, okay, I don't know how much detail I'm going to present, but okay, these are the supersymmetry. Well, and we are going to consider this massless scalar fields and massless spinors. Well, these are the supersymmetry transformation. This is the Killing spinor written in Poincaré coordinates. It's quite simple. It's coordinates. And then, as usual, we can expand both the scalar field and the fermion fields near the boundary. Those here you have these alpha and beta functions, and then for the fermions we have eta minus and eta plus. And then by applying this expansion in this supersymmetry transformation and using the explicit form of the Killing spinor, you get like this supersymmetry transformation rules for these functions alpha, beta, eta plus, or the components eta plus and eta minus. So notice that, for instance, now you have different possibilities to have supersymmetric boundary condition. For instance, you have alpha equal to 0. Recall that I was Neumann, Dirichlet boundary conditions for the scalar. So if you want this to be invariant under the supersymmetry transformation, you could demand that the component eta minus has to be 0, and then eta minus equal to 0 remains invariant if alpha was 0. So alpha 0 with eta minus 0 is a supersymmetric boundary condition. Similarly, you can define a supersymmetric Neumann boundary condition. So this is here. So we have, you see, you have these two possibilities preserving 4 supersymmetries. You can impose Dirichlet or Neumann boundary conditions. Actually, what we want to do is we can have some mixed boundary conditions. The most obvious thing you could try first is just a combination of chi alpha plus beta. You can do that. You can find that with this other mixed condition for the fermions, this is supersymmetric, but if you do that, you also need to require that the Killing spinor is constant. And then you have to to kill two possible supersymmetries of the problem. So this is one of the reasons why this is not good for us. And another reason is this here, since alpha and beta has different dimensions, chi is dimension full, so this is going to break conformal symmetry. So, well, can we have mixed boundary conditions without breaking scale invariance? Recall that alpha and beta have the scale dimensions that differ by 1. So what we just simply propose is to combine beta with the derivative of alpha. So, and in that case, the parameter is dimensionless. And moreover, when you consider this mixed boundary conditions for the fermionic components of fluctuations, you don't need to restrict at all the Killing spinor, so you preserve 4 supersymmetries. So just in order to emphasize the importance of being this interpolate of this mixing parameter dimensionless, you can use these boundary conditions to compute correlators holographically, as in the usual way, solving by the scalar fields, and now solving with boundary conditions with sources, like in here, compute the compute the action on shell, and taking the derivative with respect to the sources. When you do that for the mixed boundary, what we call type 1, the mixed boundary conditions with this dimensionful parameter chi, well, what you get is a complicated correlation function, which is not consistent with a CFT. So on the other hand, when you repeat the same with this type 2 mixed boundary conditions, where now this chi parameter was dimensionless, what you get is like a correlator, a 2-point, which is perfectly admissible for a CFT. So, but let me say that, well, there is like an extra twist in the kind of type 2, in the kind of boundary condition that we wanted to consider. And the reason is the following. So this type 2, which is the second example we discussed, it interpolates between Neumann, beta equal to 0, and the derivative of alpha equal to 0, the time derivative. So if you wish, this is like interpolating between Neumann and something where we call a smearing or average of Dirichlet boundary condition, because this is indicating that phi has to be constant, but without specifying the actual value of phi naught. So to actually interpolate between Dirichlet and Neumann, we need to further fix this phi naught. And the way we did that was to replacing the mixed boundary condition for the scalar by this kind of integrated version of it. It's a bit awkward, but at least it fulfills all the requirements. So somehow that was our main result. So these other type 3 boundary conditions preserved for supersymmetries. They interpolate between Dirichlet and Neumann, and the interpolating parameter is dimensionless. So that was our proposal, that this kind of boundary conditions can be used to account for this zeta-dependent family of supersymmetric Wilson loops in ABJM. We did a further check. We computed the one-loop correction to the open string partition function. And despite using these chi-dependent boundary conditions, the one-loop correction was actually independent of chi, was actually vanishing. And this is consistent with the fact that the Wilson loop is independent of this interpolating parameter. So, well, before jumping to the summary, let me just mention that what I will discuss how would it be if the theory, if we have here a marginal deformation, there must be a marginal, exactly marginal operator. So you can interpret the Wilson loop as the expectation value of the exponential of the marginal deformation times zeta, sometimes some parameter. Expanding to small zeta, you get like, you're gonna have the integral, and this operator is receiving two contributions. One of them I called here OV, is like just the product of two scalar fields. But then you have also this OF, which is like the integral of two fermionic operators. So I just wanted to stress that we had non-local boundary conditions in the dual description, and now the candidate for the marginal operator is also expressed in a non-local fashion. So, but one should try to check whether this OB plus OF is exactly marginal. You see that already at one loop, there is an ABJM vertex that allows them to mix, but you should verify that it has vanishing anomalous dimension, or maybe even better, maybe you could try to use supersymmetry to verify that this combination is exactly protected. So let me, I'm almost there, so let me just summarize. So, well, what I just presented for you, it was how mixed boundary conditions in ADS2 can be used to describe either randomization group flows in a one-dimensional defect theory, or even marginal deformations of D equal to 1 defect theory. Okay, this is of course an old idea. What I got just discussed is new and concrete examples of it. So, and to be more precise, I discussed different, I classified them at type 1, type 2, and type 3, but the last one, the one what I call type 3, was a mixed non-local and supersymmetric boundary condition in ADS2, we argue that this is the way you could account for this supersymmetric family of zeta-dependent Wilson loops you have in ABJM theories. And let me just conclude with some open questions. So it could be interesting to understand better the exact form of this exactly marginal operator in the line. It could be nice also to see if it is possible to identify these other types of boundary conditions with some other Wilson loops in ABJM theories. We can consider now what I would call it like defects in the line. So you can, in a line, you could, the only defect you could consider is like a domain point, which is like a sudden change in the definition of the parameters of the line. So if you wish, it's like a cusp in this parameter zeta. So an change in an abrupt change in zeta could, sorry. An abrupt change in zeta could lead to an anomalous dimension. Can we define like a kind of a sort of Stralsund function associated to it? Could it be computed exactly? Can this help to establishing a relation between the parameter in the field theory, in the Wilson loop, and the parameter in the dual boundary condition, or even if it is possible to construct these mixed boundary conditions with dimensionless parameter in higher dimensional ADS spaces. So I think this is all what I wanted to say. So thank you very much for your attention.
Thanks a lot, Diego, for this very nice talk. And maybe there are questions or comments already.
I have two questions. Oh no, one question. What about the case of zeta greater than 1?
You are okay. I could. I think. Well, you are talking about the ABJM case or the n = 4.
ABJM case.
Yeah, I guess that. Sorry, where is it? Here. I guess that it is still supersymmetric, and it's part of this family as well. I don't see any reason why you should restrict yourself to.
Yes, exactly. So the question is, what happens in string theory?
Oh, in the string theory. Well, sorry. I don't have an exact picture. I mean, in order maybe to answer that precisely, we would need to know a better relation. I mean, in a better way, how zeta is related to chi in the. So in the boundary conditions, in the dual description, we don't have chi. We don't have zeta. We have chi. So you could ask what happens when chi goes to zero to infinity. So yeah, but it's not clear how to account for zeta going to infinity in this. So I guess that in order to answer that question, we need, I mean, to establish some relationship between zeta and chi. But I guess it's
you don't really need that.
You don't need.
No, because you say that you identify the 2 points of zeta equals 0 and zeta equals 1, and you identify these 2 points in terms of chi. Now I'm asking, if I take zeta beyond 1, where would you take chi?
Yeah, because I see, yes, that's right, because somehow zeta equal to 0 is chi equal to 0, because that corresponds to the Neumann boundary condition, and zeta equal to 1 is chi going to infinity. So yeah, it seems that when chi goes from 0 to infinity, you are just exploring the range of zeta between 0 and 1. Yeah, well, yes, I had to think. I mean, it's not clear how to describe that other limit. I should think more carefully about it. And but it's a very interesting question.
Some other comment or question?
Sorry, I have a general, it's not a question, it's more a confusion. So can you explain a little bit again about this kind of normalization of the Wilson loop of Polchinski and Sully that you mentioned in the beginning? So my confusion is the following. So I have this Wilson loop, and can I define, does it make sense to define it away from the fixed points? Or should I just define it at the fixed points in the field theory? So can
you can define it for
then what does
any
it mean?
value of Z.
Right. And then the fact that it runs, it means that if I consider a probe that is very close or very far from the Wilson loop, the probe sees a bosonic or fermionic Wilson loop. How do I physically see this running?
So when you mean when you say proving, you mean like inserting an operator in the line, or?
Yeah, I guess that's my confusion or what I'm asking. So when I have, say, a 2-point function, I take nearby points, I probe the UV, right? I take faraway points, I probe the IIR. So I can see the flow by just moving the points. But here you have a Wilson loop. It's already a big circle or a big something, and now you're saying it runs. So does it run with respect to the? Can I see this running by taking a probe and making it approach the Wilson loop, or going far from the Wilson loop, and then the probe would see the Wilson loop being bosonic or supersymmetric? That's how I should think.
Yeah. Well,
if I want to convert the flow into something physical, how should I think?
Yeah, I'm not sure. I mean, if I understand your question, the question on how to answer it. Yeah, the flow. I mean, you see by when you need to renormalize this set of parameter, but yeah, I don't know. I don't see how to translate this with.
Sorry, shouldn't you be able to see this from the one-point functions of the transverse component of the stress tensor? That should change under this this defect.
Yeah,
this defect.
One way. I mean, one way you could see it. I mean, when you for instance consider the insertions of and you compute it like the 2-point correlators of 2 operators inserted along the line. For instance, when typically what you do, you can do it with the dimensional regularization, and then you have like this deformation of the dimension. You have this epsilon parameter that takes you away from. So when you do like the computations at one loop, typically you can read the anomalous dimension from the coefficient in front on the 1/epsilon expansion of this. But when you go to 2 loops, typically what it happens is, well, you get like 1/epsilon square poles in the expansion, but they have to cancel. I mean, typically, I mean, again, even you have 1/epsilon square, they are eventually they have to cancel, and you read the anomalous dimension for these insertions from the 1/epsilon, and then you realize that when you are not in one of the fixed points, you have like to expand this this zeta coefficient with a 1/epsilon term correction, in order to, when you go to the 2 loop computations, to cancel these two this second order pole you have in 1/epsilon. So this is quite technical. So I probably this is not answering.
Yeah, I wanted to see more some interpolation by considering some physical observable that would really.
I think you can just change.
But I think. I mean, I think the Wilson loop will have a scale, right? So
right.
This zeta parameter will introduce a scale after you include the running. And then if you consider, for example, a small Wilson loop, you will have the UV result, just the ordinary Wilson loop. And if you have a very big Wilson loop, for example, you will have the result corresponding to the other boundary condition.
So this zeta is dimensionful?
Yeah, there is dimensional transmutation because it runs. I mean, it starts out being dimensionless.
Classically, it's dimensionless, but once it starts running, yes, it's dimensionful.
Yeah, like there is a paper by Simone, which basically says that this expectation value of circular Wilson loop acts like a G function or C function for this defect. And it was kind of later more rigorously argued by Nishioka and others. So also from that perspective, you can just change the radius and see the interpolation, or you should be able to see that.
And then very large Wilson loops would be supersymmetric, and very small would be bosonic.
Right.
Okay. Okay, thank you.
Okay, so we have moved already to the discussion session a bit, but well, let me just ask super quickly a comment, because you did it also in the paper, but maybe on the role of these massless fermions. What is the story, if there is a story? It looks like an interesting story, but you said it's, so this is a question for Diego.
Yes.
Yes.
So, well, I think that, I mean, where is it? I think it's here. So the study of supersymmetric, if you wish, boundary conditions in ADS2 is an old paper by, what is it? By Sakai Tani. Yes. But they discussed only Dirichlet and Neumann. And again, I mean, even in Polchinski and Zule, they kind of conclude that the only supersymmetric boundary condition they could consider were the just Dirichlet, but because they have always massive fermions with mass 1. Actually, I don't think even there is two possible quantities. I mean, there is like a notion of Brestelone-Freeman window for the fermionic fields in ADS. And then I think you have two admissible quantization for the spinor fields when the mass of the spinor is between -1/2 and 1/2. So I think when you have spinors of mass 1 in ADS, I think the only sensible quantization is like Dirichlet or the ordinary. So I think that's one. But so that's why in the case of having this massless fermionic excitations in the case of ABJM, this opens the possibility of having Neumann, supersymmetric Neumann boundary conditions and even mixed boundary conditions. Yeah, I don't know, no. Valentina, if what was exactly your question?
No. I think yes. It's just a question of boundary conditions again. So they just ask for other boundary conditions, which are the good one.
You see, I mean, if your fermion were not massless, so they can. I mean, the supersymmetry analysis is completely different. So, for instance, here these two behaviors are exactly the same, but typically they have like d/2 minus m or d/2 plus m, but being massless, they are the same. So if you start considering massive fermions, is completely different, and then so. But somehow it is crucial that to have massless fermions in this example to have other possible boundary conditions.
Thanks. And I think the relation to integrability or localization, you don't have strong comments, possibly.
No, well, I could say some. I mean. It's another article. It's a paper I studied with Matías Leoni, Sol Luque. We consider the integrability of that was in the case of if you wish the Polchinski-Zule interpolating Wilson loop. I mean, we already knew that the locally supersymmetric Maldacena-Wilson loop Wilson line was supersymmetric, but what we did was to study perturbatively in general, and then we realized that the other endpoint, the other conformal points, the ordinary Wilson loop, at least perturbatively, is integrable. One loop. So, but I don't know whether this is just an accident, of a one loop result is still is kind of interesting, because in the I mean, you have like you would be like observing for the zeta equal to 0 ordinary, the Wilson loop in n equal 4 seems to be integrable. At weak coupling, we checked in this scalar sector, but also strong coupling, because strong coupling is an open string with Neumann boundary conditions. So you have somehow integrability at the very weak coupling and a strong coupling. So I think it is very interesting to try to see whether integrability will persist or not in this other case. I mean, but I don't know if there is any deep relation or between integrability and being conformal, because or maybe this is also just an accident that, well, the theory is integrable only at the conformal point of this Archie flow. And in ABJM, Sorry, say it again.
No, I think I'm just, yes, I'm responsible for this delay of the discussion session, but please just finish with what you were saying.
No, then that was concerning integrability in N equal 4 theory. You could ask the same in ABJM. The question of integrability of the Wilson loop in ABJM is an old and elusive question so far, but I mean, yeah, at least that, I mean, we are trying to do with Victor Giraldo Rivera at least some perturbative computations now to analyze the integrability of the Wilson loop, and then you can try to ask the question in the bosonic Wilson loop in the half BPS, or now you could even try to see whether this full family of Wilson loop is integral or not. At least let us start. You could start with the perturbative computation, but so far we don't have anything to report yet.
Okay, thanks a lot again, and I move everything to short